So right now we're going to take a look at what some definite integrals represent. So the first integral is pi times the integral from 0 to pi over 2 of cos squared x. So if we take a look at what the integral is saying, we can try to figure out what it means. So we can take a look at this cos x squared term, and this is very similar to the form integral pi, for example, y squared dx, where y is the height of a function, and this integral is with respect to x. So this function, or this form of an integral, is basically saying take a curve specified by y, for example, this curve y, and rotate it from a to b, rotate this section or this area about the x-axis. So if we were to rotate this section about the x-axis from here to here, you would get something like this, some shape like this. And this entire thing specifies the volume of this shape. Now here I've just drawn some random function, but if we were to arrange this into this form, then we can get perhaps a better understanding of what this integral is trying to accomplish. So right now we're going to see if we can do that. Right now we see pi cos x squared. So why not let our y be cos x, because it is already squared? So we can take this and rewrite this as pi, the integral from 0 to pi over 2, cos x squared dx. So right now we can have our radius be cos x. Now this is what we're going to use to rotate the function across the x-axis. So if we were to draw the function, we have our x be the horizontal axis and y be the vertical axis. If we have our function cos x here, then what we're going to do is have our r be cos x wherever it is on the graph. So we're going to go from 0 to pi over 2. So this is x equals 0, and this is x equals to pi over 2. So essentially, we're finding all of these areas of circles here, and we're going to add it all up to find the volume of this shape. I'm going to see if I can draw it better here. So we're going to try to find the volume of this shape, obtained by rotating this piece of cos x across or around the x-axis from 0 to pi over 2. So what this is saying is you have x between pi over 2 and 0, and the y is going to be between cos x and 0 as well. So the area bound by this region is rotated across or around the x-axis. So this is what this integral means. We're taking cos x between 0 and pi over 2 and rotating it around the x-axis and finding the volume. Right now we're going to go take a look at our second example. What does pi times the integral from 0 to 5 of y dy represent? Well, this is very similar to our previous case, except right now, instead of having our radius be cos x, we're going to have our radius be plus or minus root y. Because if we square this, then we get y, and we essentially get back to our original form. So if I draw a graph for this, if we draw the graph for plus root y, and if we let y be the horizontal axis and x be the vertical axis, we're just switching things around here. It really doesn't matter what we name our axes. If we let the function be plus y, plus root y, then it's going to look like this. But if we rotate this around the y-axis, it doesn't really matter if it's plus y or negative y. So if we take this, this function from 2 to 5, let's suppose that this is x equals 2 and this equals x equals 5, then it doesn't matter whether we use plus or minus y. So just for simplicity or convention, let's just use plus y right over here. So x equals plus root y. So what does this represent? Well, similar to the previous example, our radius here is root y, and we're finding the area of the circle at each point and adding it together to find the volume of this shape. So essentially, we're taking the area underneath this curve over here, and we're rotating it around the y-axis. So another way of writing this is the area bound by x is between 2 and 5, and I'm sorry, this is actually y. Y is between 2 and 5. So y is between 2 and 5, and x is between the functions, because we've actually switched our axes around. So y is between 2 and 5, and x is between root y and the origin, or not the origin, the y-axis. So that's just x equals 0. So this is not y. This is going to be x equals 0. The area bound by this rotated around the y-axis. So if you take a look at this and compare it to the previous result, you can see that it's quite similar. Just the axes are rotated 90 degrees and flipped. So if we go to our third example, this one is pretty interesting. We have the difference of two squares. So a way to think of this is we have two radiuses. Here, let's do this. We have two radiuses. One is r1, and we'll let that be the radius of this function. So we'll have that be y squared, and we'll have the radius of our second one be y to the fourth. So if we take a look at a graph of these functions, where y is the horizontal axis and x is the vertical axis, we can sort of see that y squared is going to be something like this from 0 to 1, and y to the fourth is going to be below that from 0 to 1, and they're going to be both 1 at y equals 1. And we know this because if we take a smaller number to a higher power, it gets even smaller. So by taking smaller numbers to higher powers, the y to the fourth function should be less than the y squared function. So this represents the area from 0 to 1 underneath y to the fourth, which is this lower one, minus the area underneath the function y to the 8th. So it is actually, right now we have here x equals y squared. And here we have the function x equals y to the 4th. So in fact, we're taking these functions and we're spinning it around the y-axis. So in a sense, we're spinning the entire area underneath this y squared function from 0 to 1. And if we do that, we're going to get something like this, this big pointed cone-like shape. And we're going to take that and then we're going to subtract the volume obtained by rotating underneath the y to the 4th function. So, in a sense, what this is equivalent to is if we had, let's use a different color here, if we had this area and we rotated it around the y-axis, then we would have that volume of the shape be equal to this integral. So another way of writing this is we are going to take y between 1 and 0. So this is in fact the area bounded by y between 0 and 1. X is actually between these two functions. So x is less than y squared, which is less than y to the 4th, and rotate that around the y-axis. Y-axis. Okay, so this is in fact basically the previous two examples, just one volume subtracted by another. So if we go to our final example, which asks us what the integral of 0 to pi over 2 of two squares added together represent, well, I think there's an error here. This actually is a subtraction sign. So let's go on and fix that. So this is going to be subtracted 1. This is basically just the same thing as our previous example. So what does this represent? Well, consider our R1 to be 1 plus cos x. Let our R2 be 1. And right now, if we draw the graph, we'll have 1 plus cos x be something like this, something like that. These will be our axes. X is the horizontal and y is the vertical. And our second function here is going to be the constant function, R2 equals 1. And you know, these keep going, but the only thing that we are concerned with right now, this intersects the x-axis at 2, or the y-axis at 2. This line intersects the y-axis at 1. What we are concerned with is the things that happen between x equals 0 and x equals pi over 2. So what we have here is similar to the previous example. We're going to take the area from 1 plus cos x, starting at 0, going to pi over 2. We're going to take this area, entire area underneath of here, and we're going to rotate it around the x-axis. And we're going to take that volume, and we're going to subtract the things that are under 1. So we're going to use a different color to represent that. So we're going to subtract this area under 1 from 0 to pi over 2. So essentially, all we get is this blue area, which is this. So we have this area over here, and we want to rotate that area around the x-axis. So we're going to get something like this. And it's going to be similar to a donut. So it's going to be like a ring with a hole in the middle. So if I were to draw it somehow like this, you would have this shape going across and around with a hole in the middle, which the x-axis passes straight through. So what does this represent? So this represents the area bound by the region between 0 and pi over 2. And our y is going to be between 1 plus, whoops, didn't mean to do that, 1 plus cos x, and between 1, this is rotated around the x-axis. So what we're going to have now is the volume obtained by rotating the area bound by these conditions, and we're going to rotate that around the x-axis to obtain our answer.